In this video, we're going to discuss gravity, the fundamental force of attraction that all objects with mass have for each other. Here's our formula for the force of gravity. It is equal to big G, which is the universal gravitational constant. It is this value with these units. This is not meters, this meters cubed, kilograms, second squared. You're not plugging in values here. These are units, just like 65 miles per hour. This is like miles per hour. This is just units. Then we have mass 1, mass 2, so it'd be mass of the first object times the mass of the second object, divided by the distance squared. Now this D is for distance, not diameter. That's a common misconception. It's a common problem. People put in diameter for D. D is distance. It's actually distance from the center of the first object to the center of the second object. So let's work through a problem using this equation. What is the force of gravity between Earth and you? Earth's radius is 6,378 kilometers. Now we can just use Earth's radius and we can ignore the distance to the center of your mass. Because you're so much smaller than Earth, it really doesn't matter. And Earth has higher and lower points, so we're going to just go for an average here that you would likely be at 6,378 kilometers from the center of Earth to the center of you. The problem here is that we have kilometers. Over here in our gravitational constant, we can look to this for units that we want to use. We want meters. Meters is also the standard SI unit. We're always going for the standard SI unit here, so we want 6,378 times 10 to the third meters. I knew to change it to this number from here because kilometers, the kilo, means times 10 to the third. Anytime you see kilo, you can replace the K with times 10 to the third. Then we have Earth's mass. And then we have your mass. Now for the big M here, mass 1, we'll plug in Earth's mass. It could be either one, but for right now we're just going to go with M1 is Earth's mass, and M2 is your mass, and we'll keep using that for the rest of this video. Force. Here's our 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. We just plug that in as our gravitational constant here for G right there. Then mass 1. Our first mass here, we'll put in Earth's mass. It doesn't matter which one came first, but this is the way we're going to do it. We'll put Earth's mass first in kilograms times your mass, which is about 77 kilograms, divided by the distance from center of the Earth to the center of you in meters. And this right here, squared. This is common mistake. Don't forget to square your distance. People forget it all the time. Don't forget to square it. And if we plug this into our calculator correctly, we should come up with 753.74 meter kilograms per second squared. This is also known as a Newton, meter kilograms per second squared. You could replace this with a capital N for Newton, but I like to stick with the units to where everything's broken down for us so we can see what we did to get here. So let's see what we did to get here to meter kilograms second squared. We have to cancel our units. We have to remember that they always cancel. What's on the top can cancel with what's on the bottom. So here we have meters squared and meters cubed. Well, 2 m's go away here. Take 2 away from this one. That leaves us with 1 m. Now we can get rid of 1 kilogram. That kilogram. And seconds can't cancel out anywhere, so we're left with meter kilograms per second squared. Right here. Or newtons. So 753.74 newtons. So this is the force between Earth and your body. But what if what about the acceleration? Because we're not so concerned with the force. What we really want to know is what is the acceleration. So we can use an equation that we're all familiar with, Newton's second law. Force is equal to mass times acceleration. If we rearrange this a little bit to solve for acceleration, for the A, we divide both sides by m, and we get A is equal to, or acceleration is equal to force divided by mass. Okay? Then we just plug it in. We use the force between the two objects, right? The force that we feel is 753.74 newtons divided by our mass. We want to use our mass because we want to have our acceleration, right? What kind of acceleration do we have towards Earth? So we have to use our mass. And we come up with, look at this, 9.81 meters per second squared. This number right here should seem very familiar to you. This is the constant we use for our acceleration towards Earth, 9.81 meters per second squared. But is it always 9.81? A question that's asked a lot is, if you drop a hammer and you drop a boulder, which one will hit the ground first? Well, if they're both dropped in the same spot or in the same area, will they both hit the ground at the same time? Well, let's find out. We can rearrange these equations to prove it. Here's the two equations we used. All right, so let's replace this F with what this F is equal to. We'll make them equal to each other. All right, so before, when we did this equation, we used, for this m, we used our mass to get our acceleration. So we'll call this m2 to go with our mass up here, m2, and this will be the acceleration that we feel. So if F is equal to ma, we can replace this F with ma. So m2a, or mass 2, or our mass, times acceleration is equal to the gravitational constant times the mass of the planet times the mass of us divided by distance squared. We can do some canceling here. We can cancel our mass on this side with our mass on that side. So now the mass of us, or the hammer, or the boulder, none of it matters. Acceleration is equal to gravity times the mass of the planet divided by the distance squared. So the acceleration due to gravity is the same for all objects on our planet. The equation to the left here is proof. But when I say all objects on our planet, that's not necessarily really true, because the distance can change from the center of the Earth. If our distance would change, which would change our acceleration, if we're down at sea level or if we're at the highest mountain. So how would that change? If our d was much smaller, meaning that we're down at sea level, this is much smaller, which would make our acceleration much what? Larger. If our distance is much larger, like if we're on the top of a mountain, the acceleration would become much smaller. So the distance from the center of the Earth would definitely make a difference. But as far as what masses we're dropping, those canceled out. They make absolutely no difference. That is it for gravity.